Hello everyone, welcome to a new lecture in the series of Deep Learning for Control. In this lecture, we will be focusing on reinforcement learning or RL. Here is the overview of this lecture. We will be starting with a brief introduction to approximate dynamic programming or ADP and the different ideas for approximation, such as approximation using pruning and approximation using neural networks. Then we give an introduction to RL where we relate it to ADP as well. Approximate dynamic programming is an algorithm which is used for solving optimal control problems. And in the lecture series on LQR, we have studied that we can solve optimal control problems using dynamic programming. And ADP normally uses dynamic programming algorithm with approximated cost. We can consider a general nonlinear system in discrete time as in equation 1, where F is the nonlinear mapping which transforms the current state to the next state under the control action UK. Now we can consider an optimal control problem with the quadratic cost function as in equation 2, where the cost is summed across n time instants. And this QK and RK are the weighting matrices for the state and control inputs. Let's say our objective is to find the optimal control input sequence which minimizes this cost function. Then this problem can be solved recursively in time using a cost to go function Vk as in equation 3. This Vk is the cost to go from the time instant k till the end, and it can be represented as the current cost, which is xk transpose qk xk plus uk transpose rk uk plus the cost to go function from the next instant, which is denoted by Vk plus 1. In general, in dynamic programming algorithm, the optimal control input can be computed, which minimizes the cost to go function. And here we will be using this current cost or the running cost plus the optimal cost to go function from the next instance, which is Vk plus 1 star. In the lecture series on LQR, we used a cost to go function like this. And in the case of linear systems with the quadratic cost function, we were able to represent this cost to go function as a quadratic function. And that's why we were having an analytical solution for the optimal control problem, which made this entire cost to go function as a quadratic function. Here our system is nonlinear, therefore we will not be able to represent the cost to go function as a quadratic function. And we do not have an analytical expression for the cost to go function as well. Since we do not have a closed form expression for this Vk plus 1 star, solving this problem will be difficult. One possible solution is to try all the possible state and control pair and compute this cost to go function for all the state and control pairs. We have to discretize it over the entire state space and control space. This will become computationally intractable when the dimension of the state vector and the control vector increases. And this is also known as the curse of dimensionality, which makes the dynamic programming intractable for nonlinear systems. One possible solution to the curse of dimensionality is the approximate dynamic programming or ADP. In ADP, we use as approximation to the cost to go function or the value function. This approximation can be denoted by Vk hat, and this Vk hat can be computed offline in most of the cases. Then the control input at each time instant is computed by solving the approximate Bellman equation. Here, instead of Vk plus 1 star, we will be using Vk plus 1 hat, which is an approximation. And by minimizing this cost function, we can always able to find the optimal control input. This is the central idea of approximate dynamic programming or ADP. And there are different ways for approximating this value function. One of the simplest ways to approximate it using piecewise quadratic function, where we have a set of positive definite matrices P1, P2 till Pm. And here we can find the optimal matrix which minimizes this quadratic function. Here we have only a finite possibilities for the matrix P. And such problems will occur in integer quadratic programming, mixed integer quadratic programming, and piecewise quadratic approximation for nonlinear programming. In such cases, the idea of pruning can be used for reducing the size of this particular set. The pruning is based on the idea of redundancy, and the matrix Pj in this set is called to be redundant with respect to the set P. If we remove that particular matrix from the set, then the minimum cost does not get affected. As an example, we can consider a case with two positive definite matrices P1 and P2. For P1, the cost can be plotted in black color in this figure. We have plotted x transpose P1x, where x1 is taken along the x-axis x2 along the y-axis and x transpose px along the z-axis. Similarly, for P2, we have plotted the cost x transpose P2x in red color. And here we have the plot of the ellipse which is obtained by x transpose Pjx equal to 1. And this curve can be obtained by taking the intersection of this curve with a plane parallel to the xy plane for which the z coordinate is constant. And here we can see that the cost for P1 is always lower than the corresponding cost for P2. And if we see the ellipses, the ellipse for P2 will be in the interior for the ellipse for P1. In this case, we can see that if we consider the minimum cost, then the matrix P2 is redundant because P1 is always gives a minimum cost for any state x1, x2. In this case, we can remove the matrix P2 from the set without affecting the minimum cost. However, if we consider another case such as P1 and P2 as in this case, for P1 we have the cost in black color and for P2 we have the costs in red color. Here we can see that for some states P1 gives the minimum cost and for other states P2 will give the minimum cost. In this case, if we consider the ellipse for P1 and P2, we can see that the ellipse for P2 is not in the interior for the ellipse for P1. In this case, the matrices are not redundant. Now, one idea of pruning is to remove all the redundant matrices from the set, which will reduce the set P. And thereby it reduces the computational cost as well. In relaxed dynamic programming, the idea of redundancy is extended for alpha redundancy, where we use a relaxation factor alpha, and the matrix Pj is said to be redundant. If we remove the matrix from the set, the cost will be bounded by alpha times the original optimal cost. And here we can see that if we consider P1 as in this case, we have the cost will be in the black color. And if we consider P2 as 1.5 times P1 and P3 as 2 P1, cost for P2 and P3 are shown in red and green color. And here we can see that as we are increasing this scaling factor, the cost is increasing and the size of this ellipse will become smaller. In this case, we will remove all the alpha redundant matrices and this will result in more number of redundant matrices and thereby reduce the size of the matrix P. But here the optimal cost will be increased by a factor of alpha. And in the case of dynamic programming with relaxed pruning, another idea of epsilon redundancy is introduced. Here the idea is that even if we remove Pj from the set, the optimal cost will be increased by a factor of epsilon times mod x square. Here this time we can rewrite as x transpose P plus epsilon I x. We consider an example with the three matrices, P1 as this matrix, P2 as P1 plus 0.1 times I, and P3 as P1 plus 0.5 times I. And for P1, this cost is in black color, and for P2 it is red color, for P3 it is in green color. Here we can see that as we are increasing this scaling factor, the chances of the matrix become redundant increases, or in other words, the size of this ellipse will decrease. This will also result in an increase in the optimal cost by a factor of epsilon times mod x square. These are some of the ideas which we can use for reducing the computational complexity. And another way is we can also use approximation with the neural networks, where we will approximate the cost curve function using a neural network FNN. The function will take the current state as the input, and this will result in a value approximation where we use neural networks. The neural network can also use for approximating the control policies, where this mu of xk is a function of the state vector, and this can be called as a control policy. And we define this control policy using a neural network. So which means like we can use neural network either for approximating the cost function or to approximating the control policy. This idea is extended to reinforcement learning, where the different algorithms are based on these two approaches. Next, we move from ADP to RL or reinforcement learning. ADP can be considered as a control theory equivalent of reinforcement learning. ADP is conventionally used in process control, robotics, adaptive control, etc., where a system model or a partial knowledge of the model is available. RL is a more recent approach which is introduced for solving games such as chess problem or in the autonomous systems and robotics, etc., where the system is unknown or too complex. Most of the RL algorithms uses either model-based ADP or model-free ADP, and it can be grouped as value iteration methods, policy iteration methods, and hybrid methods. And this value iteration focusing on estimating the value function similar to the ADP case. It is used for estimating the cost to go function using some neural network algorithms. And the examples are Q-learning and SARSA. Policy iteration focus on directly improving the control policy. Here we will be approximating the control policy using some neural network models. And the examples are proximal policy optimization or PPO, reinforce, etc. And in hybrid methods, we will use both the value and policy approximation ideas. And the major example is the actor critic methods. In deep reinforcement learning, we use deep neural networks for either value approximation or policy approximation. And deep reinforcement learning algorithms are extensively studied in the literature, and these are used in various control-related applications. That leads us to the end of this lecture. Thanks for watching.